test. Which is typically pretty wordy, but we'll get to the gist of it and I think we'll understand what's going on. Okay, I think I will erase our picture. Come back to something if we need it. All right, we're going to start with let C be a critical number of a function. And we'll call that function f that is continuous on an open interval. And they call that open interval I containing C. Okay, so C is a critical number of the function. The function itself is continuous on an open interval. Notice it didn't say differentiable, it said continuous on an open interval I that contains C. So if that open interval I were like A comma B, once again, C would be somewhere in between A and B. I won't say in the middle because I don't want you to think it's exactly in the middle, but it is definitely somewhere in between A and B. All right. Now, if F is differentiable in the open interval, and here's the glitch of it here, except possibly at C. And the reason it's except possibly at C, we got C being a critical number. But what are critical numbers? Critical numbers satisfy the condition that either the first derivative is undefined at C or the first derivative is equal to 0 at C. If the first derivative is equal to 0, well then the function is differentiable there because I was able to get the answer of 0. But if the first derivative is undefined, it would still constitute a critical number, but I have to state that it's a possibility that maybe that's the situation going on here, and that F maybe is not differentiable at that value that is my critical number C. Okay, so this is going to work whether that critical number is derived from setting the first derivative equal to 0, or whether or not that critical number is actually a point on the function still, or value on the function where the derivative is undefined. So either way. So if I'm thinking of a point on a function and the derivative at that point is undefined, one of the examples that comes to my mind would be the vertex of an absolute value function. Or anything at all that would be the location of a cusp. Those points are sharp points and they're not differentiable, and yet they are critical numbers of the function because they are defined within the function. Okay, so let's keep going on that. Except possibly at C, then f of C, and what does f of C represent? Represents the y value of the function at C. So we're talking about the height of the function at C. Then f of C can be classified as follows. Okay, so first situation, okay, f of C, okay, we'll say if f prime of x, that means my first derivative, changes from positive to negative. And for positive, I'm just going to write a plus sign. From positive to negative, I'm just going to write a negative sign. If f prime of x changes from positive to negative, let's think about that. F prime, which is my slope, is changing from positive to negative. We're going positive, and then all of a sudden we're going negative, and yet we are continuous, right? We're continuous. The function is definitely continuous. So the only way that we can go from positive to negative is to go right through that high point. So what do you think f of C is going to be called? It's going to be a relative maximum. So if f prime changes from positive to negative, then f of C, which is the y-coordinate at C, is definitely a relative positive to negative. It's a relative maximum of f. Definitely a relative maximum of f. And the second case, I bet you're going to guess it anyway. If f prime of x changes, I like to say switches, you'll hear me write switches more than changes, from negative to positive, then f of c is a relative minimum of f. Let's just look at that. If f prime is changing from negative to positive, so the function itself is decreasing and then increasing, we have to hit our relative min. Same thing up here. If we're increasing, the function is decreasing, it has to go through the relative max. All right, what do you think the third case is? If f prime of x actually equals 0, okay? F prime of x actually equals 0. I suppose I could say, I don't want to say equals 0. We'll say if f prime of x does not change sign, then f of c, well, if it's not changing sign, can't be a relative max, otherwise we change from positive to negative. Can't be a relative min, otherwise f prime would be changing from negative to positive. So all we know is that f of c is neither a relative max nor a relative min. Okay? So we're changing from positive to negative. Okay? This is a positive slope, this is a negative slope, and this up here is my relative max. This is a negative slope, this is a positive slope. Anytime we're changing from a positive slope to a negative slope, even if it's like this, positive slope, negative slope, we still have to go through our relative max. If we go from a negative slope to a positive slope, negative slope here, positive slope here, we have to go through our relative min. Same thing, absolute value function, or maybe we have something that does something like this. Be weird, still function. For each x, there's exactly one y, so here we'd still have a cusp. Either way, negative slope, positive slope, relative min is in the middle, negative slope, positive slopes of the tangent line, relative min is in the middle. If we have no sign change, then f of c is neither a relative max nor min. Let's say the first derivative is positive, 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 positive. Here's a critical number where the slope of the tangent line is 0, and then I go positive, 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 positive again. Slope of the tangent line was positive, slope of the tangent line is positive. This point right in here is neither a max nor a min. Not a relative max, not a relative min. So this happens to be everybody's favorite thing to play with. I like the second derivative test, we'll get to that in the next section, but right now our first derivative test is what we're going to practice using. Okay? Now I'm going to do, I think, 2 examples for you and then we're going to wrap it up.